All right. So we left off on Monday talking about the Vedic and talking about the original mechanistic proposal where you go through a beta-ene. Let me go up to that. And then that beta-ene cyclizes to give you oxyphosphatane, which decomposes to give you the alkene. But we also talked about this proposal by Vedas that says that the betaine doesn't exist. Um, and so his proposal is that rather than going through a betaine, that it goes through this four center transition state that we have shown here, right? Where you have um, one particular transition state with the R group. You can see that the R group is pointed up, right? And the other transition state, which is shown down here, where the R group is pointed equatorial, it's in an equatorial fashion, right? And that particular transition state is said to be disfavored. So the the original idea for the transition state was that it was planar. Let me just show that right quick. Right, because these two transition states shown here are what we call pucker. You can see how it's kind of like it's even though it's a four-member ring, it's kind of drawn like a chair. And yeah, so it's kind of drawn like a chair, but that's to alleviate steric strain. And I'm going to show you why and what happens if we consider that this is planar. So this is what the planar transition state would look like prior to it being puckered and trying to alleviate any strain. All right, so this would be the R group that's on your aldehyde. And then you have your R group. Let me draw this and kind of bold this out. Then you have your R group here that's on your illet. And again, the goal is to minimize steric strain. So those groups they want to be apart from one another. They don't want to be on the same side. All right. And so with the phosphorus, you have, of course, those three phenyl groups. Sorry about that. And then you got another phenyl group here. Right. So the reason that this is planar and not puckered, the reason it adopts that puckered conformation is a couple of things. The first is here. So you have a 1,3 interaction, it's similar to a 1,3 diaxial interaction, like you would see in a six-member ring. And a steric interaction that's going to increase the energy of that conformation. So that's why one of the reasons why it's puckered. Right. That's why it doesn't just adopt this planar conformation, but it actually bends so that you can alleviate some of those reactions I'm sorry, some of those interactions. And then you also have here was being termed as a gauche interaction between this phenyl group and oxygen. And if you remember from organic one when we learned about like chairs and Fisher, I keep saying Fisher projections, Newman projections, and chairs. You know, the gauche interaction is something like if you have a staggered conformation. Let me redraw that. If you have a staggered conformation like this, and you have a group here, let's just say R1 and R2, this is gauche, right? So they're also proposing like this gauche interaction, right? So with that gauche interaction and the 1,3 interaction that's between the phenyl ring and the R group, the favorite conformation for this four-member uh, cyclic transition state is to be puckered. And so that's why I have it drawn like that. You can see the oxygen is kind of pointed up instead of being planar to avoid that interaction with the phenyl ring, and then the other phenyl ring here is also able to avoid that 1,3 interaction with that R group, right? So this pucker conformation is energetically more favorable, right? So let's look at another type of illet, and then we're going to look at the transition state for that and why we see what we see. So for what's called a stabilized illet, let me give you an example of that, and then we're going to look at this other example. So a non-stabilized illet, let me show you the difference between those two, and then we're going to go back and look at some more of the Wittig reaction. So something like this would be considered non-stabilized, right? Keep in mind that this is, you can also write it like this. Right, so the stabilization part is talking about stabilizing the pair of electrons on carbon. Right, so a stabilized illet is going to have some type of electron withdrawing group on that carbon to help stabilize that charge, right? So a stabilized illet would be something like this, where you have something like an ester or something like that. So this is what we would consider a stabilized illet. So the ester is going to stabilize that carbon. All right. And there are other types of stabilized illets, but we're gonna look at we're just gonna look at this other example. All right. So for a stabilized illet, one of the things that you're able to do differently with a stabilized illet is that you're able to favor one particular stereoisomer over the other in the product. So you're able to get, uh, in some cases, trans selective or cis selective. It depends on the stabilizing, whatever the stabilizing functional group is. And we're going to talk about that a little bit later. But I want to show you this other example uh, from Vedas where they looked at stabilized illets and they also looked at the transition state to justify why it's trans selective or why it's cis selective. So let's look at that. So let me show you their example. Right. So here's the illet that they're working with. It's a I'm gonna run out of room. Give me a second to move this to the next page. All right. Right. So this is the illet that they're working with. And you can see right away one of the things that they've done is they have added in this ring system to kind of force the phosphorus part of the illet to be planar, right? So they eliminated a lot of those interactions that were present in the other transition state where the phosphorus was just acyclic with three uh, phenyl rings attached to it, right? And so in doing that, they're also able to kind of control the steric interactions that happen in the transition state. So this is here plus, right? And so what they propose now for the transition state is here, right? And then the methyl group that's here is equatorial out here. Let me fix that up. Right. So you can see right away that in this transition state, uh, there are no steric interactions other than this 1-2 interaction right here between hydrogen and R1. But this is the favorite proposed transition state, right? And what that leads to is this oxyphosphatane here, right? Where the methyl group is here and the R group is here, which leads to a trans alkene, right? So that's the proposed. Let me Let me put the rest of this in here. That's the proposed transition state. Right? And all of the phosphorus piece is all planar, so it's all flat. So you got no interactions with that. You got no interactions with the other group that's attached to it, and only the 1-2 interaction between uh, R1 and H. Now, let me ask you a question. Why do you think what? Okay, so what would the other version of this transition state look like? Right? What happens if I draw it this way? I'm just going to copy it if I can. And I'm going to see how you're thinking about this. All right. What happens if the approach of the aldehyde is different, right? And instead of uh, what happens if in this version of the transition state? What do you think? Do you see any potential problematic interactions? What do you think? I see something, but I want to see if you see it. Right? Obviously, this is going to be less. I mean, still a 1-2, but it's not going to be as prevalent. But what do you think about the interaction, the potential interaction between the ethyl group here and R1? Right? And it's those type of subtleties that allow one transition state to be favored over the other and allow one product to be favored over the other. All right. Anybody got a comment on that? What do you think? Do you think that's going to drive the energy up some compared to the transition state up top, where the R group is away from that?
Yeah, I think it will increase the energy.
Yeah.
I think it's less favorable.
Yeah. Some of it's going to drive the energy up a little bit, even if it's not drastic. But you got to think in terms of uh, what in terms of these types of reactions, 1 kilocalorie difference can be the difference in one product being favored over the other. Right? That man makes a huge difference. Uh, and then you also have the issue of here, where you have now an interaction between R1 right here and then the methyl group. Let me extend this out some so I can write that in. Right, you're gonna have like a pseudo gauche interaction there. So right, so you'll have a like a pseudo. Let me put that hydrogen back in here. right? You'll have a Gauche interaction here between the CH3 group and R1. So sorry about that. So that transition state is going to be a lot more destabilized. So that destabilization. That's what's going to cause the trans to be favored for this illet, right? Because the energetics. I'll show you that in a second. But the energy to get from or to this transition state is going to be the activation energy is going to be more. And with that, if that's the case, then the other product is going to be formed faster. So I'm going to show you that in 1 second. So this is going to be destabilized by two interactions. One is with R1 and the ethyl group, and then the other one will be R1, that Gauche interaction between R1 and the methyl. All right. So that's why you only see uh the trans alkene in this case. That's why it's favored, right? And you'll see again they give another example, which I'll show you, uh, where the illet is just a simple illet like that plus, right? And what they propose again in the transition state. I mean, I'll go this way. Darken that up some. And again, so here's the phosphine, and you got a ring here and then another ring here, right? And they're showing phosphine basically in kind of like a trigonal bipyramidal geometry. And so this is going to lead to this oxyphosphatane, again, where the trans product is favored. Right, so this is going to also give you the trans product. All right. And again, it's all based on this overlap and the interaction between. Let me fix that up right quick. Sorry about that. The interaction between the groups on phosphorus on the illet and the groups on the aldehyde. If you had to draw the second transition state for this, how would you draw it? Right. So how would you show the aldehyde if it came in? Let's say it came in from the opposite face, from its opposite face.
It switched to the equatorial position.
Which group? The R.
Yes, sir.
Yeah. So you R1 will be equatorial, and then what happens then? Right now you got a big interaction between R1 and the ester, right? The ester group that's already equatorial. I'm gonna leave this open ended on the note so you can draw it in. I'm gonna leave that page blank. All right. So let's look at um some other examples of the Vedic, and we'll talk about like some of the stereochemical outcomes. Um, and then we're gonna come back and look at some stabilized illets and talk about the differences there. Right. All right. So any questions before we move forward?
No.
No. All right. So let's look at a few more examples from the Vedic, and then we're gonna come back and talk more about those stabilized illets. Right. So for the Vedic, if you can have a aliphatic illet or an aromatic illet, which is again talking about stabilized and non-stabilized. So for the aromatic illets or the stabilized illets with the Vedic, so if I react this with an aldehyde or ketone, doesn't matter, right? I get the trans alkene and an 85 to 15 ratio, trans to cis. Right. Well, so in this case, my aldehyde is aliphatic, right? What that means is that it's saturated, right? There's no double bonds, no aromatic rings, nothing like that. Um, if I take an aliphatic illet, which is I'll show that here, or non-stabilized illet, and I react it with a aldehyde where or as aromatic, I can I'll change the stereochemistry there also, right? I can take an aromatic aldehyde and an aliphatic illet and generate the cis alkene in a 90 to 10 ratio. 90 to 10 cis to trans ratio, right? So the way this is explained is this. So for if you have a stabilized illet, the explanation or the justification for the trans stereochemistry is that you get what's called a late transition state. What that means is that the reaction itself is endothermic, and you get a late transition state. And so the trans is what's it's the kinetic because you got a competition between the trans pathway and the cis pathway. So for stabilized illets, trans is what we call the kinetic. Do y'all remember that from organic two? Kinetic versus thermodynamic product.
Somewhat.
All right. Yeah. So I'll explain it in a little more detail in a second. But the trans is kinetic, and then um, it's a late transition state. Right? Do y'all remember the Hammond postulate? Y'all remember that from part one when we talked about thermodynamics? Jonathan, you did you take part one from Abdallah?
Hello?
Yeah.
What did you say?
I said, did you take part one with Abdallah?
Yes.
Okay. So when we say something is a late transition state, that means that the products are gonna resemble the transition state. And if we say it's an early transition state, that means that the reactants are going to resemble the transition state, right? So, and I'll put this here in parentheses so you can go and refresh on that, right? So if that's for stabilized illets, and then if you have a non-stabilized illet, like an aliphatic illet, then we say that the cis is the kinetic product, right? And it's an early transition state. All right, so let me give you an example of what I'm talking about. So we're talking about early transition state versus late. If it's early, that means that the transition state is closer in energy to the product, right? Remember on any reaction energy diagram, you have your transition state here, and then you have reactants and products. So the transition state, if it's early, it's going to resemble more of the reactants than it does the products, right? That's based on the Hammond postulate. And then if it's late, that means the reaction is more endothermic and the transition state is closer in energy to the products. So the TS is going to resemble whatever is closest in energy to. Right. So you have if you show your reaction coordinate or your reaction diagram, right? Remember, energy is on the y-axis, and then time is on the x-axis, right? So then, when you think about this in terms of kinetic versus thermodynamic, let me show you that because what you have to have in the case of the kinetic product or the thermodynamic product is you have to have an intermediate uh, that's common like to both products, right? They don't come from two separate places. They come from the same intermediate, but the decomposition of that intermediate or the conversion of it into one product or the other is what's going to determine that. So you basically have like, and we'll talk more about probably talk more about this on Friday after we do our um after we do our papers, right? So for the kinetic product, right, if you have a intermediate, some intermediate, and you have a competition between two different pathways within that reaction mechanism, right? That's when you see this idea of a kinetic product or a thermodynamic product, right? So for the right, and so the kinetic product is not necessarily the most stable either. Some it's just the one that has the lowest activation energy. So we'll call this P1 and we'll call this P2, right? But if you look at the activation energy, and it doesn't have to be a lot, it can just be a little. It can be 1 kilocalorie or half a kilocalorie, right? So this is going to be your transition state, and then this is going to be your activation energy to get to that transition state from the intermediate, right? And if you look over here, you can see that the activation energy is a little bit less, right? So the kinetic product is going and the whole point of saying all this is that there's a way you can control uh, the kinetic versus the thermodynamic. There's a way you can control it based on what functional groups are attached to your illet, right? If the illet is more stabilized, then the you're able to control the rates of the reaction and bring down the energy of the transition state, right? And then that favors the thermodynamic product, or that changes the product distribution, right? So with that being said, if you look here, you can see that uh, the pathway to P1 is lower in energy. Let me fix those. Fix that. It looks kind of sloppy. Right. So this is uh, the pathway to P1 is lower in energy. So a lower activation energy means that it's the fastest form product. right? So that's how you get your kinetic product, right? It's the one that's formed the fastest when there's a competition between two pathways. And then the other part of that is what we call the thermodynamic product, which is the more stable product, right? So if you look over here, you can see that P2 is lower in energy than P1, right? Even though it takes more activation energy to get to it. And so you have to do something to the intermediate or to the start material so that when you get to the intermediate, you're able to either lower that activation energy to access P2, right? Or have the ability to go from P1 back to the intermediate and then convert to P2. So we're going to talk more about that on Friday. Anybody have any questions about anything?
No, sir.
All right. So I'm gonna post this. Are y'all able to access that playlist with the lectures on it? I just want to make sure that I'm because I had that playlist as unlisted, but I just want to make sure that when you click on the link, you can see all the lectures and not just the one that I sent.
Yeah, I can see
I can
it.
see it.
Okay. So let me know if you have any problems with accessing those lectures or accessing the notes. And then the notes will be on Blackboard, but also the handout that I was working from with the different proposal from Vedas and from Peter Whip. That's also, I think I put in the announcement the other day where you can find that. Were you all able to find that?